Okay, very good morning to everyone. I hope you can hear me clearly and can see the screen also clearly.
Yes, sir.
Good morning, sir.
Morning, sir.
Good morning. Thank you very much.
Good morning, sir.
Okay, so yesterday there were two very long videos with regard to the previous topic, special electrical requirements on board oil, gas, and chemical tankers. So I deferred it for today. This one puts everything very comprehensively in a nutshell. Okay, whatever we spoke about, all the various explosion proof ratings, then where they are going to be kept, what are those zones that we talked about, zone 0, 1, and 2. All these are going to be explained in this particular video. So it is in your interest to pay special attention to this. Also with regard to the labels that are there for your explosion proof rated motors or light fittings in the hazardous regions. I told you the examiner will give you one particular thing like that and ask you to explain what each thing means. Okay, at that particular point, I will pause the video and I will point out what I mean with regard to that. Okay, so we'll see this video. There are two videos. This one followed by another one where maintenance is done on explosion proof motors and explosion proof lights. Okay. Quite often they have asked, how would you carry out your maintenance on a routine maintenance on your motor? You have to change bearings, isn't it? Okay. So how would you go about that? It will be explained over here. Your light fitting, you have to change a bulb or something in one of these explosion-proof rated light fittings. How would you go about that? Because anyway, you have to open it up, isn't it? So accordingly, they will be explaining over that. Also is a rather long video. So I've kept it for this morning where your minds are fresh and can absorb everything. Okay. So we'll go ahead first with this video.
Objectives for this training module are combustion fundamentals, fire and explosive requirements, explosive limits, auto ignition and flashpoints, explosive groups, IEC classifications, temperature classifications, methods of protection, and electrical device markings. A combustible gas or dust explosion may exist in a variety of industries, including petrochemical and refining, food processing, pharmaceuticals, and fossil fuel power generation. The vast majority of organic and synthetic materials, as well as some metals, can form combustible dust. Combustion or fire is a chemical reaction in which a combustible material combines with an oxidant to release energy. Part of the energy release is used to sustain the explosion by utilizing existing heat or creating a vacuum to consume more oxygen. Within a hazardous environment, there are three elements necessary for a fire or explosion: a combustible material, also known as a fuel, ignition source, either electrical arcing or general heat, and an oxidizer, also known as oxygen. When a fuel, oxidizer, and ignition source are present at the necessary levels, burning or explosion will occur. To reduce the possibility of fire or explosion, one of the key elements needs to be reduced or removed. Another key factor in a fire or explosion are the explosive limits. These are the maximum and minimum concentration needed of a given combustible material to support a fire or explosion. To form an explosive mixture, the hazardous gas must have sufficient concentration levels. The minimum concentration of oxygen to combustible material is known as the lower explosive limit, or LEL. If the concentration is below the LEL, it will not be flammable or have enough flammable material present. The same condition would apply if gas concentration is too rich, meaning it will not ignite because it will not have sufficient oxygen to sustain the fire or explosion. This is known as the upper explosive limit, or UEL. It should be noted that different gases will have different threshold limits. In this example, the LEL of hydrogen is 4%, and the UEL is 75.6%. Therefore, any mixture of hydrogen and air that falls between these limits will have a flammable mixture. In addition to the explosive limits, each hazardous material will have an auto-ignition temperature and a flash point. The flash point is the temperature at which the material will generate sufficient quantity of vapor to form an ignitable mixture. As the liquid is heated and reaches the flash point, auto-ignition could occur. An auto-ignition is the lowest temperature at which a combustible material will spontaneously ignite in a normal atmosphere. In this example, we have the heating of a combustible liquid. Explosive vapors are created as the material reaches the explosive limits, creating the flash point. If the general atmosphere is increased to the auto-ignition temperature, fire or explosion will occur. To simplify the specification of electrical devices into hazardous environments, IEC classification methods utilize auto-ignition, flash point, and explosive limits to place the hazardous materials within groups. The two predominant methods used for classification of hazardous environments are the NEC and IEC standards. IEC and NEC standards both classify the level of risk into three main categories: continuous, occasional, and not normally present. All three categories provide the likelihood of an explosive atmospheric condition within the general environments. Within the IEC standard, the general risk categories are then classified as zones. This reflects the physical material that could provide a potential fire or explosion. For liquids and gases, the area classifications are Zone 0, Zone 1, and Zone 2. By altering the physical material to dust or fibers, the area classification numerical value changes to Zone 20, Zone 21, and Zone 22. Referring back to the necessary requirements for an explosive triangle, we know we need an ignition source, oxygen, gas, and/or dust combustible material in the correct mixture within the atmosphere. In order to specify electrical devices and hazardous locations, we need to identify the general zones within each area. When working with liquids or gas, we locate the most hazardous or flammable location directly above the material. Due to the possibility of the valve leaking at the top of the containment structure, we must classify the area as Zone 1. As we move further away from the possible explosive atmospheric condition, the zone classification would be reduced to Zone 2. By altering the combustible material properties to a solid form, the area classification above the material would be Zone 20. If the dust escapes the same failed valve, the external area around the containment unit would be classified as Zone 21. As we continue to move away from the containment unit and with reduction of category risk, the new classification for the general area would be Zone 22. Now that we know combustible materials, whether liquid, gas, and/or dust, will have different upper and lower explosive limits, and we understand the general heat could be the ignition source, within the IEC standards, the T rating specifies the maximum surface temperature an electrical device will create. As the temperature increases, the associated rating will decrease, meaning less heat will have a higher T rating, while an increase in surface temperature will reduce the T number. As a recap, the IEC standards classify hazardous areas as environments that could contain explosive vapors, gases, and/or dust within the atmosphere. The primary categories provide the risk levels as constant, occasional, and not likely. Since elements have a variety of flammability and the physical properties could be different, IEC standards segment the types of combustible materials into zone classifications. The most hazardous is Zone 0 or Zone 20. By reducing the risk level to have occasional explosive atmospheres, the zone classification is Zone 1 or Zone 21, and further reduction of category risks would change the hazardous classification to Zone 2 or Zone 22. Let's take a look at each method of protection and the general application. To ensure safety in a given situation, equipment is placed in protective level categories. As mentioned before, Category 1 is the highest safety level, making Category 3 the lowest risk and safety level. The general 8 protective methods are flame-proof enclosures, sand encapsulation, pressurization, oil encapsulation, general encapsulation, increased safety, intrinsic safety, and non-sparking. The flame-proof method is a type of protection where devices that are capable of igniting an explosive atmosphere are built inside an enclosure. This protective method prevents the transmission of the explosion to the external atmosphere surrounding the enclosure. This method of protection would be suitable for applications on power-operated equipment, switchgear, motors, and any equipment that produces an ignition source during normal operation. Sand encapsulation is a type of protection in which the enclosure of the electrical apparatus is filled with a finely granulated material. This ensures electrical arcs occurring within the electrical apparatus will not ignite the surrounding atmosphere. Pressurization is a method of protection by which the entry of a surrounding combustible material is prevented by maintaining a protective gas within the enclosure. This is generally accomplished by creating a higher pressure within the enclosure than the surrounding atmosphere. This protective method would be used for any power-operated equipment. Oil encapsulation is a type of protection in which the electrical apparatus or part of the electrical apparatus are immersed within an oil-based fluid. The general application for this type of protection would be used for switchgear units, circuit breakers, and transformers. Encapsulation is a type of protection in which the device that could ignite an explosive atmosphere are enclosed within a resin. The material used would be resistant to environmental influences, heat, and or sparking from electrical components.
Okay, I'm pausing the video over here. You can see the original PCB. Remember, I had mentioned with regard to those temperature sensors that are coming, the temperature sensors that are located within the cargo oil tank, the connections come on top. So you will be having a sort of a PCB over there, and you can see this brownish thing. That is the resin they are talking about. Okay, so basically the entire thing will be covered with this resin, or sometimes a gel, or sometimes even wax. Okay, like your candle wax also. Okay.
The general application for this protective method would be used for electrical circuit boards, miniature motors, and valves. Increased safety is a type of protection where measures are taken to prevent the possibility of high temperatures and the occurrence of ignition. This method includes the interior and external portions of the electrical apparatus. The general application for this protective method would include connection and distribution boxes, luminaires, measuring instruments, and devices that do not normally produce ignition within operation. Intrinsic safety is a protective method to ensure that the available electrical and thermal energy in the system is always low enough that the ignition of the hazardous atmosphere cannot occur. This is achieved by ensuring that only low voltages and currents enter the hazardous area, as well as all electrical supply and signal wires are protected by safety barriers. The general application for intrinsic safety would be used for measuring and control engineering, data engineering, and low electrical valves. Non-sparking equipment and wiring process is a protective method where apparatuses are designed with low power levels and low stored energy. This ensures that an arc produced during normal functionality of the equipment or as the result of equipment failure has insufficient energy to ignite the hazardous atmosphere. The general application for non-sparking protective methods would be used for motors, lighting, junction boxes, and electrical equipment. All equipment certified for use in hazardous areas must be labeled to show the type and level of protection applied.
Okay, so here they will be showing on a motor. Okay, and pay particular attention to this. Okay, those markings that I mentioned, safety markings with regard to electrical fittings within the hazardous region. Okay.
In this example, we will review a fluorescent light
Okay, so
fixture
this
within
one,
a
for
hazardous
example,
environment.
the examiner might give you something like this. Okay, so he'll tell me what each one means. Okay, so just pay attention to this.
The first identifying mark will reflect the apparatus group by hazardous application. A 1 would indicate usage for coal mines, while a 2 would indicate general industrial environments. The next identified mark is the category risk level. As mentioned earlier, there are 3 category risk levels that would identify the occurrence of an explosive combustible material. The next mark identifies the type of combustible material within this hazardous environment. The available option would be the letter G for gases or the letter D for dusts. The next mark identifies this fixture as manufactured to meet the European standards. The next letter indicates the type of protective method used. Referring back, the letter D would suggest the electrical device utilizes a flame-proof enclosure. The next number and letters will identify the explosive gas group. Remember, the gas group provides the critical information on the combustible material's explosive properties. The final marking provides the maximum surface temperature of the fixture during operation. In summary, hazardous locations could exist in multiple industries. The geographical location will dictate the general method used for classification. The European Standard, or IEC, provides guidance of risk into 3 main categories. These risk levels are then divided into zones and have numerical values that relate to the possibility of explosive gases or dust present within the atmosphere. Because combustible material could have a variety of explosive limits, the method of protection will be important. Nevertheless, all electrical devices placed within hazardous environments will follow the device markings to ensure fire or explosion does not occur.
Okay, so we'll see the next video with regard to maintenance.
Subscribe to our channel. By clicking the subscribe button, click the bell button and enjoy the latest uploads from our channel.
This is Programme 6 of VideoTel's series on practical marine electrical knowledge. The series is made up of 8 programmes. Programme 6 deals with special electrical practice relating to vessels designed to carry flammable cargo. It also aims to develop a greater awareness of the safety elements and design features built into the electrical system of such ships. We shall also show the special electrical equipment certified for use in hazardous areas, demonstrate the servicing of a flame-proof light fitting, and the method of fitting a cable gland to a flame-proof motor. There are many system variations around, so it is most important that you become familiar with the components of the electrical system and the layout of the main switchboard immediately you join a ship. Pay particular attention to the layout of the emergency switchboard. This study will pay dividends during a blackout or when troubleshooting the cause of a major breakdown. Now we must emphasize electrical safety. The golden rule is, before any work is done on an electrical installation, first isolate the circuit by removing the supply fuses or locking the circuit breaker in the open position so that the circuit cannot be energized accidentally. Then post a warning sign to alert others that the circuit is being worked on. Then prove the circuit dead with a voltmeter or an approved line tester. A switchboard can never be considered dead unless all AC generators connected to it are stopped, locked off, and all other supplies are disconnected. These points can never be emphasized strongly enough. The electrical rescue procedure is described in Programme 1 of this series. A variety of instrumentation on board ship guards, controls or monitors the ship's functioning. The red shaded areas on this drawing show the hazardous areas relating to the electrical code of practice, which is the subject of this programme. Generally they are coffer dams next to cargo tanks, compressor rooms and pump rooms, and about a 3-metre periphery surrounding all outlets for the flammable cargo. As far as the electrical system is concerned, the problems here relate to the cables going through these areas and the servicing of electrical plant operating therein. Also, they involve the use of intrinsically safe electrical instrumentation and equipment. As a general recommendation, hull returns and neutral earth systems are not normally allowed except in the case of some high voltage systems of 3.3 kV and above, where the circuits are not allowed in any dangerous area. Also, the generating plant, switchboards and battery systems must be separated from the cargo tanks by a gas-tight cofferdam. Cables laid along the foredecks should be installed in steel piping in such a way as to allow for any structural movement of the ship without strain or chafing. These rectangular expansion boxes house a loop in the cable runs to allow for expansion. The piping to and from the boxes also allows for the expansion movement of the ship. Through runs of cables may be permitted through pump rooms, cofferdams or enclosures next to cargo tanks, provided they run in heavy gauge steel piping with gas-tight joints. Cables which are associated with intrinsically safe equipment must be separated from all other cables and clearly identified as such. Here, the blue color code is used. They will have their own separate power supplies and a Zener protection barrier. The Zener barrier ensures that the maximum preset voltage in the circuitry cannot rise above the prescribed safety level, which ensures the certification of intrinsically safe, EXI. EXI, or intrinsically safe equipment and circuitry, has a protection technique which confines the energy within the system below a level which is capable of causing an explosion in a dangerous atmosphere. EXD certified equipment is flame-proof and relies on the integrity of its encasement to withstand any internal pressure of an explosion without any flame being emitted. EXP type equipment, on the other hand, is equipment which is protected by a pressurized inner atmosphere made up of air or inert gas. This prevents the possibility of a dangerous air-vapor mixture entering the enclosure of the electrical apparatus. Examples of these are seen here. Light fittings in hazardous areas must be of flame-proof or pressurized types. These light units must be on at least 2 independent final branch circuits, so that one may be disconnected for maintenance, while the other supplies enough light for safe access. Switches for these lights must be double pole, interrupting both supply lines, and must be situated outside the hazardous area. The maintenance of a flame-proof light fitting involves 2 specific objectives. First, the prevention of any deterioration in the equipment's safety level, and second, ensuring its correct, safe function. Use only non-abrasive materials for cleaning. Lightly grease, then wipe clean the flanges before fitting them together. Periodic maintenance inspection and cleaning will necessitate the inspection of all flanges, glassware and cementing to ensure that they are within the certified safety level. If either the cementing or the glass envelope appear damaged, do not try to mend or replace either. The whole fitting has to be replaced by a new part obtained from the manufacturer. It's important to remember that there is a great deal of difference between flame-proof and weatherproof fittings. Do not put a gasket between the flanges of a flame-proof fitting to make it weatherproof. This will invalidate its flame-proof certificate, as will any other modification of the original design. When reassembling these types of fittings, extra care must be taken to ensure that the flanges are clean. The special flame-proof cable gland must be checked for tightness and the electrical connection made. Again, ensuring that the conductor is held tightly in the terminal box. There must be no loose wire strand left in the terminal box. Solder the strands of a multi-strand conductor to eliminate the possibility of short circuit and ensure a secure connection. When tightening any bolts or nuts holding flanges together, the force used should not be more than necessary to prevent loosening by vibration. Excessive force may cause undetected fracture of a bolt, a casting, or other parts of the securing mechanism. If a broken stud has to be removed from a blind hole, great care must be taken to avoid damaging the internal thread or drilling through into the flame-proof enclosure. Broken or missing screws must be replaced by ones of the same diameter, thread, length, type, and quality of steel. Finally, check once again that the flame-proof gland is correctly tightened. Remember, the installation must not be changed in any way for any reason, as this may invalidate its certified safety level. Electrical motors which drive cargo pumps or compressors are housed in the motor room, and they're separated from the compressor room by a gas-tight bulkhead. The drive shaft has to be fitted with gas-tight glands where it passes through the bulkhead. The motors are required to be the pressurized type or increased safety EXE construction. The starters and the control gear for these motors must be housed elsewhere, outside the hazardous area. The motor room is pressurized so that gas or vapor may not enter the airspace where the motors are operating. Entrance to the motor room is through a system of double doors controlled by a pair of micro switches and a safety light indicator.
Hello.
The system should ensure that one door is opened only when the other is shut. When a cable run is laid to a flame-proof motor, special attention must be given to the preparation of the cable end and fitting the special flame-proof gland onto the cable. Here, the required length of the outer sheath is stripped off to reveal the steel armouring. Allow plenty of time for this work and use sharp tools. The armouring is then cut round with a wire cutter and pulled off. A further short piece of the outer sheath is stripped back, as you see here. This will free a further length of armouring, which will be clamped between the double rings of the gland for tight and secure fitting. Use special flame-proof glands which have longer threaded flame paths and rubber seal rings with extended hold on the cable, forming another flame path. Carefully dismantle the cable gland and secure the threaded base unit in the terminal box. Fit the lock nuts on the cable then the double rings for gripping the steel armouring. Fit the conical rings below and above the loose armouring, like this, ready for tightening. Temporarily remove the rubber seal ring from the terminal box port and feed through the cable. Tightening the two pressure fittings with a spanner. This will ensure that the two conical rings grip the armouring tightly. Remove the cable from the terminal box and replace the rubber seal ring. Prepare the conductor ends for receiving the terminal lugs and feed through the cable again into the terminal box. Now the conductor ends are fitted into crimped lugs and the cable connected to the terminals. Check that the lugs hold the cable tight so that they will not vibrate loose when the motor is operating. Nuts are tightened sufficiently to avoid becoming loose due to vibration. Finally, check their labels to ensure that all portable apparatus, such as portable radios, torches, or insulation resistance testers, are specially approved, intrinsically safe types, certified for use in hazardous areas. If you use portable electrical equipment or tools, ensure that their connections and cables are sound and safe to use in the area in which you intend to use them. This concludes the subject for Programme 6.
Okay, so that was with regard to those special